Welcome into the Backroads Bill podcast. I'm Ben, and last week's episode, I said that today's episode was going to rock. And to keep up with that promise, we brought onto the show a guest who knows everything there is to know about rocks. He is a professor emeritus of Queen's University. He's making his second appearance, actually, on this podcast. We are pleased to bring on Larry Dyke, and we're talking today about the geological landscape of Northern Ontario, how it was formed and how the Ice Age and other events helped shape the hills and mountains and valleys of Northern Ontario and beyond. We also take a look at the future and how things like climate change are going to affect the way that this land will be in hundreds of years. And most importantly, Larry gives us his favorite rock puns, which was definitely not the reason why we wanted him on the show in the first place. We get to all of that exciting stuff in a moment, but first a word from this episode's lead sponsor, Voyager Aviation. Founded in 1968, Voyager Aviation is a proud member of our community, providing worldwide aviation services from our headquarters right here in North Bay. If you're looking for a challenge, change, or want to expand your current career in aviation, Voyager is hiring for a wide range of technical and non-technical roles, including pilots, aircraft maintenance personnel, corporate administration, machinists, supply chain professionals, and more. Be part of a workforce that is over 400 strong, supporting humanitarian, government, defense, and civil aviation operations around the world. For a career in aviation and beyond, learn more about open positions and career paths at voyav.com. So today, for the second time, we are honored to be joined by our guest, Larry Dyke, who is Professor Emeritus from Queen's University and a longtime member of the Geological Survey of Canada. The last time, Larry, you were on was February 7th when we talked about potholes, not the kind you find on the road, but the kind you find in nature. That was the 22nd episode of this podcast. Larry, how are you today?
Oh, boy, very well. Yeah.
And you're coming from the West Coast. You are from the area, but you moved out west. So this is very early in the morning for you. So again, thank you for joining us.
Oh, not at all.
All right, Bill, you were very excited about this. And when I asked you, what are we going to be talking about? You said a word that I don't even know if I can pronounce. So why don't you start things off?
Yeah, Ben, the word is geomorphology, and that's a lot of syllables. And I'm just wondering, if you took much of that in high school or beyond. But having Larry on the show, we're going to try to make some sense of the landscape, the superficial landscape of Northern Ontario and underneath the ground, because mining's so important in Northern Ontario, and of course the extensive picture of all across Canada. And that no better person, I think, is to have Larry, and of course he's going to draw upon his vast array of experiences and with other colleagues and try to, again, some burning questions I have about certain features of Northern Ontario that he can help explain to the listeners. Because on the Backroads Bill podcast, we go to many, many places, and of course, it's all about sense of place, and that place is often dictated by the physical landscape. So, Larry, welcome again, and I'm looking forward to really unlocking some of the questions of that 4.543 billion years of age that the planet is. But back to you for a second, Ben, as we transition into this show.
Yeah, we had some interesting conversation before we started recording. Some stuff about climate change, and one of the things that I wanted to ask you, Larry, just about geology in general was there's so much stuff that you can figure out through geology. How, just quickly with the climate change stuff, and I know we were talking about the jet stream, but how does the climate change, how does that affect, how does geology, I should say, affect climate change, and how as you as a geologist can see those effects in your field?
Geology provides the record for climate, and I guess that's the relationship there. So the climate produces the geomorphology, as Bill's just mentioning. So geomorphology is just the study of how the form of the earth comes to be. In other words, the river valleys and the mountains and deltas and so forth. So we geologists, we use geology to reconstruct the climate, to see what it was like in the past. And we have to combine geology. In other words, say a sedimentary record in a lake over the last, like since the end of the last ice age, and that lake has been receiving sediments, and there's lots of examples of this in the North Bay area, where people have taken cores from the lake bottom, and you get layers of sediment, of mineral sediment, and you also get organic layers, peat layers, and something called gycha, which is a Polish word for sort of an organic mud. And those, any organic layer, of course, you can date that with the carbon-14 technique. So you can put together a picture of, what was going on to cause those sediments in that lake. That's had a lot to do with knowing how the drainage has changed in the North Bay area. But also, you can look at the pollen in those organic sediments and reconstruct what the vegetation was like. And this has been done extensively in North America for the period of time since the end of the last major ice advance. So the Laurentide ice sheet, that's the ice sheet that covered North America. So it extended, well, not all of North America, but it's extended well down into the U.S. As that withdrew, of course, plants began to recolonize, and we have a really good reconstruction of the vegetation in North America over the last 18,000 years. And from that, you can deduce or you can hypothesize what the climate was like and how it changed. So geology kind of provides a record of climate. At different scales. Geology, in geology, you get the most detail for the most recent time periods. As you go back further and further and further into the past, the resolution becomes less and less. So we can tell things on a year-to-year basis, say for the last several thousand years. But what Bill was talking about, near the birth of the Earth, if you like, we're looking more like a resolution at, say, 10 million years. And part of the reason there is just there's been so much time for the records to be obscured by other processes that we can't see as much detail into the deep past.
Whether it's 10 million years or the most recent ice sheet, the Laurentide ice sheet, then that's what I want to dive into with regards to Ontario and Northern Ontario, because often when I explain in my stories, I talk about the James Bay lowlands, the Hudson Bay lowlands, then, of course, the Canadian Shield, which is probably the most prominent feature in Canada. And then when we start looking at Northern Ontario, we've got that kind of uniqueness of Manitoulin Island and the extension of the Niagara Escarpment. And then as we move down kind of to Southern Ontario, it's flatter, sometimes referred to as tablelands. And then, of course, all those, the height of land, which we've talked about in the past in some of the written stories in village media. So again, I don't know exactly where we should start, but give us your take on how, as it is in the present, what Northern Ontario is like now, and probably, again, for our listeners and viewers, that, the last ice age was the thing really we need to kind of understand, because that could happen again, and if it did, there would be other changes. But let's just start about the Northern Ontario landscape and transitioning a little bit into Southern Ontario.
Well, Bill, I can almost extend that to the entirety of Canada in terms of your question about, how has the landscape come to look as we see it today. And you're absolutely right. It's the last glaciation, so what we call the Laurentide glaciation, which extends over about the last 40,000 years, but it was just the most recent in a series of glaciations that extended back about 2 million years. So this is the Pleistocene, sort of the last era, or most recent era of the Earth. And really, the landscapes that we see across Canada are a function of what those ice sheets did. And both with their advance and the erosional effect of the ice and so forth, and we have to think that say at the extent of the last ice age, 18,000 years ago, I mean, the ice was about up to 3 kilometers thick, say over Hudson Bay. And of course, it's moving laterally, spreading out, especially to the south. So there's an enormous erosional ability there. But also when that ice started to retreat, started to melt, you had enormous quantities of meltwater and flowing all over the place, south into the U.S. and of course east through the Great Lakes and out the ancestor, the St. Lawrence River, carrying enormous amounts of sediment and so forth, and depositing it, and so that's what we see today. Now, of course, that's all superimposed on, as far as Northern Ontario is concerned, the Canadian Shield. So, so from sort of tens of thousands of years, we're actually jumping to a time scale of billions of years. And so the Canadian Shield, as you so rightly state, is the foundation of it is the continent, really. And geologists refer to shields as the basement. In other words, it's sort of the lowest level of rock that you can, that you're seeing. And there's shields all around the Earth. There's the Brazilian Shield, and there's the Scandinavian Shield, and so forth. So these are large elements of the Earth's crust. They're the thickest parts of the Earth's crust. So when we think of the oceanic crust, it's thin. It's, say, 5 kilometers thick. The shield is 50 kilometers thick. So 10, in order of magnitude, 10 times thicker. And the Canadian Shield has been assembled over the last, basically the last 4 billion years, or say extending from the beginning of the Earth about 4.5 billion years ago to about 500 million years ago. And it's been assembled from a series of sort of subcontinents, so what we call terrains, and they have names like the Superior Terrain and so forth. So these were earlier continents. They've collided through plate tectonics processes and produced deformation in mountain ranges and so forth. So so the Canadian Shield is built up of a half a dozen or so of these smaller terrains being assembled over this billion-year-long time frame. And of course, when they came together, they collided just like India is still colliding into Asia and pushing up the Himalayas. That sort of thing was going on the Canadian Shield. So we had enormous mountain ranges, and there's been the time for them to be eroded down and produce the landscape, the subdued landscape that we see today.
Yeah. So, for instance, again, in the past, we've talked about the high points in Northern Ontario, Ishpeming Ridge and Maple Mountain. They're worn down now, but they were enormous mountain ranges, as you say, at one time.
Oh, absolutely. Yeah. And a lot of the sediment, I mean, so you're going to ask the question, well, okay, so if we had these high mountains, and they're not that high now, like Maple Mountain, 2,000 feet or so forth, compared to maybe 30,000, 25 or 30,000 feet in the dim past, where's the sediment? Well, a lot of that sediment is is underneath the prairies, the Western Canada Sedimentary Basin, and that's been building up over the last 500 million or so years, even maybe actually the last 1 billion years. You go to Waterton National Park or Banff, especially Waterton, you're looking at rocks there, sedimentary rocks that are sitting on top of the Canadian Shield that are almost 1 billion years old in their own right. So those are the erosional products from these early mountain ranges, which are long gone.
Yeah, and it's a badge of honor for canoeists and hikers to get to some of these peaks because they are high peaks, so to speak. And that also leads me then to another kind of canoeing kind of question, and we've talked about this as well. You know, that oscillating line that goes across Northern Ontario and beyond, we exclude all the political boundaries where the water flows in one direction towards James A. Hudson Bay, the Arctic, and the rest of the water flows south into the Great Lakes, St. Lawrence. But maybe tell the listeners and viewers about that, how that is actually happening still to this day.
Gosh, Bill, yeah, I mean, where the heights of land are, I mean, yeah, that's the end product of this long process of erosion that we've been talking about that has been occurring over, I mean, you know, really billions of years. The last ice age was sort of the finishing touch on that. And so with that weight of ice, you know, up to 3 kilometers of ice, that depressed the crust. You know, the crust was pushed down into the mantle by that weight, and of course that weight was removed when the ice sheet melted, and we are still seeing the lasting effects of that, what we call rebound, isostatic rebound. Isostatic meaning that the crust wants to come back to its sort of equilibrium position, and it's still happening. It's happening the fastest where the ice was thickest. So you go up to Churchill, Manitoba, the shore of southwest Hudson Bay, and the rebound is still occurring at about 1 meter a century. Now that maybe doesn't sound like a lot, but that's a very, very gentle landscape, but a very gentle slope into the ocean. So if you raise the land 1 meter, the shore retreats maybe hundreds of meters, and you can see effects of that in some of the sort of archaeological remains and so forth, like the iron rings that were installed to tie up the packets that would come in to supply Fort Prince of Wales and Fort Churchill and so forth. And no ship could get into those now, just because there's been 2 or 3 meters of rise relative to sea level of the landscape.
That's very interesting because in perspective too, we'll pick Lake Nipissing in the North Bay government dock. The estimate may be incorrect, let's say 10,000 years, that the government dock may be high and dry at that time because of the isostatic rebound.
Right. And interesting phenomenon. There's I think is it a Miskey Island in James Bay, just off, that big island in James Bay, and so it's predicted in about 500 years that's going to become part of the mainland, because the strait or the body of water that separates it from the mainland will be high. It will be dry. And so that'll become part of Ontario. It's presently part of the Northwest Territories. All islands in Hudson Bay are part of the Northwest Territories. So, just sort of an interesting political question. So sometimes politics does come into it, I guess.
So another thing, interesting, and we'll move over to Manitoulin Island, the Niagara Escarpment, how again, often when I describe Northern Ontario, Manitoulin Island is different, along with the shoreline of Lake Superior. But let's tackle Manitoulin Island and how it's unique in our Northern Ontario landscape.
Gosh, Bill, yeah, well, that's really an interesting lead into sort of what was coming after the Canadian Shield, or at least after the rocks that formed the Canadian Shield came to be, and all around the shield, and we were talking about the Western Canada Sedimentary Basin, there are other very broad, gently concave areas, and the Michigan Basin is one of them, and it's centered, between Lake Huron and oh my gosh, I'm just trying to think of the geography of the Great Lakes. But at any rate, in the center of the state of Michigan, that's a much more recent sedimentary basin. It's still pretty old. It goes back to the Cambrian, so 500 million years ago. And so the Manitoulin Islands are the very northern fringe of that basin, because the Manitoulin Islands are formed of Paleozoic limestone, so completely unmetamorphosed as compared to pretty well all Canadian shield rock. So Manitoulin Islands are the northern edge of the Michigan Basin, and they're lying on the boundary between the Manitoulin Island rocks and the Canadian Shield is what you would call an unconformity. So that's an erosional boundary between two sort of major components of the Earth's crust. And so what you have there is you have the Canadian Shield, you have a land surface which presumably was available for the start of the formation of the Michigan Basin. So those rocks started to be deposited on the Canadian Shield, and the boundary is an unconformity. And an unconformity generally is basically what it is a huge gap in the geological record, because there's a period of time that the Canadian Shield was being eroded. So that's gone. There's no record of that, or at least it's in sediments hundreds or thousands of miles away. And then you have these younger rocks being deposited on top. And there's really good examples of those all around Canada. There's some really good ones around Kingston, where you also have limestones sitting unconformably on the Canadian Shield.
What does that mean, unconformably?
Okay, it means that there's a huge gap in time between those two rock units. So you've had the production of the Canadian Shield rocks, okay, but by whatever process, you've had the erosion of them, because when you think about it, I'm just thinking, well, right around North Bay, for instance, you're driving out from North Bay towards Mattawa, and you see all the rock cuts, and there are gneisses and granites, igneous and metamorphic rocks. There's no way that those could have formed at that level, at the surface of the Earth. They had to have been formed, or the metamorphism would have to have taken place like 10 or 20 kilometers down. So there's been a huge amount of erosion to bring those rocks to the surface, along with a huge amount of time. And then you're starting to deposit younger rocks on top of that. So we have the glacial deposits of the last ice age deposited on top of the Canadian Shield. So that boundary is an unconformity. So an unconformity is just a big gap in time in the geological record.
We're going to take a quick break from Larry and all the rock talk, and I feel like my head's going to explode at points, because it's in a good way. It's just a lot of information. It really brings me back to like grade 5 science class. Again, in a good way, and I'm just trying to soak everything in. Larry's a super, super smart guy. Always a pleasure to have him on. But we do need to take a quick second to thank one of today's sponsors, the La Framboise team at Realty Executive Local Group Inc. Brokerage. And if you're in the home for a home, if you're in the market for a home, I think that's a better way to say it. They are an absolutely fantastic group that you can go to right here in North Bay. They have some absolutely fantastic people there. Obviously, Natasha Laframbois, Matt, Phil Sagan, Adam Legros. They're all ready to help you through your buying and selling experience. In today's market, it's a lot, especially for younger folks who are trying to get into the market. I know that they would definitely, once I'm ready to buy a house, they'll definitely be the first person I will go to, and they've just have so much experience. They've been providing it to the North Bay community over 17 years. What were you doing 17 years ago? I think I was, I was still in high school. That's a long time. It flies by, but it's a long time, and trust me, like there's a huge difference between going to somebody who's not as experienced and somebody who's very experienced. So their goal is to provide knowledge, support, and guidance in order to prepare your home for sale, bring it to market using multiple selling strategies, and getting it sold. If you want to know more, you can check them out on their website, laframboisteam.ca. They are always happy to help, and we are always happy to get back to Larry and all the rock talk.
So I want to lead you. I don't want to go on to this other question because I want to talk about mining a bit. But let's talk about and I'm putting it in the perspective of the layperson who drives the main roads and the back roads. But what about that terrific scenery along Lake Superior? How was that created?
Oh my gosh, the tablelands there, Bill. Yeah, no, I know what you're talking about. And I mean, let's.
They're called the Tablelands. That's the name of it.
Well, that's sort of what would you call it? A
generic term.
Yeah, a generic term. So what I'm thinking of is the Anikami Basin. Okay. At any rate, those tablelands, they're called tablelands just because the rocks are forming sort of a flat surface, like a table, and of course they've been eroded to form cliffs and palisades and whatnot. I mean, there's the palisades that you see as you turn north on Highway 11 from Highway 17 at Lake
People
Nipigon.
rock climb those in the winter.
Right, yeah. And at any rate, so those flat-lying rocks, they're sedimentary rocks and volcanic rocks there. The remarkable thing about them is that they are about 1.9 billion years old. They're flat-lying, so there hasn't really been any major deformation or mountain building over that period of time. They're flat lying. They're not deformed into folds and so forth, say like the Rockies are. And they'll be sitting on older Canadian shield rocks. So by the time those rocks that form the tablelands, and that includes the Gunflint Chert, which contains some of the oldest fossil remains that we know on Earth, the fossil algae. By the time those had been deposited, the shield was already in existence, and it's so thick that it's like a big strut or a really thick sort of beam in the Earth's crust. It's strong enough that you have compression from the sides, but it's so thick and strong that it's too thick basically to undergo any more deformation. All the deformation is occurring around the edges, say to form the Appalachians and the Cordillera, and where the rocks are thinner and more directly subjected to the pressures from plate tectonics.
Now, Ben, you're wondering about mesas, M-E-S-A. Now,
there's a lot of words happening here.
You might be thinking about the mesas you see in Arizona or I guess New Mexico, Larry. But we have them in and around that Lake Superior near Schreiber. Because
for sure.
Yeah, you can maybe explain that.
Well, if you have a big panel of sedimentary rock, And I mean, think of Monument Valley at the Four Corners area in the Southwest United States. I mean, that's another remarkable area. The rocks are quite a bit younger there than along the north shore of Lake Superior, but at any rate, they're flat-lying and they're on continental crust. So they've been lifted vertically, but that's about it. And of course, when you lift an area vertically, you produce an erosional potential. In other words, you're creating a hill for water to run down. And so those sedimentary rocks in the Southwest U.S. have been carved up by streams like the Colorado River. And the same thing has happened in the north shore of Lake Superior. You've got a flat-lying sedimentary sequence there consisting of cherts, which is like flint, and sandstones and volcanic rocks, like lava flows that have flowed out on the surface and just formed a big horizontal layer. And stream erosion is just cut down through that to form the cliffs. So you have these areas between the stream cuts, and those are mesas.
We've had Adam Schultz on the show, Canada's Indiana Jones, and of course, he in his first book, Alone Against the North, he found a river that no one had been on. It flows into James Bay, called the Again River. And his book is, and he's been on the show a couple times. But what happened in that James Bay, Hudson Bay lowlands? Why is that different? Because we talked about the Shield, talked about the Lake Superior coastline, Manitoulin. But what happened in that James Bay, Hudson Bay lowlands? And of course, it's low lying and so small. I meant when I went up to the northwest corner of Ontario, north of Fort Severn to Nunavut, and the border of Manitoba, Ontario, and we had to ford so many small and large streams. What happened there?
Gosh, Bill, I mean that we're just encountering yet another one of these broad sedimentary basins that formed on top of the Canadian Shield, basically after the Canadian Shield had finished forming. So we have the Hudson Bay Basin, and it's centered roughly in the middle of Hudson Bay, so it's underwater there. But there is a sequence of sedimentary rocks, unmetamorphosed, mostly carbonates like limestones, but there's sandstones on top of that, and so that's what underlies the Hudson Bay lowlands and the lowlands around James Bay. So basically flat-lying sedimentary rocks. And so the Ice Age would have planed those off to a certain level. And so it's provided flat, sort of poorly drained terrain. You're in an area there where you've got sort of the ideal conditions for preserving organic sediment. So you've got poor drainage, you've got lots of standing water. It's not, it's not as productive as the equatorial sort of rainforest zones, but also it's cool. So so that's why you're getting the thick organic soil accumulations. You've got near level terrain, poor drainage, and kind of a compromise between not particularly fast growth, but you've got really good preserving conditions because it's a cool climate there. So once something falls into water, that's it. It's not going to decay anymore. It's going to get preserved and contribute to the buildup of the peat layer. So that's the production of the Hudson Bay lowland, the organic terrain in the Hudson Bay lowlands, which actually accounts for about half the soil organic carbon in all of North America.
Wow, that's interesting. Now, pretty soon, Ben, we're going to have the Ontario Parks people on, and they're going to talk about provincial parks, certainly across Northern Ontario and Ontario. But Larry, a couple of the parks are named Esker Lakes Provincial Park and Kettle Lakes Provincial Park. and they're formed by different processes. But maybe for Ben, because I know he's been really bugging me to understand how a kettle lake is formed, but that's a pretty easy explanation when you think about it.
I'm still trying to wrap my head around half the stuff we've talked about today. I'm going to have to go back and re-listen to most of this.
Well, the whole point of having Larry in this episode of the Backroads Build podcast is that, we go everywhere and we should understand how the physical landscape was formed. I know it's probably not a burning question for everyone, but we really have to think about these time-honored processes that may occur again or are occurring because they're hard to see because of the chronological nature of how we look at things in our own lifetime. Our lifetime is not, in comparison to the age of the Earth, is of course very, very, very minute. But how does a kettle lake form first, Larry?
Bill, if I could just back up a titch here. There's a lot of practicality to what we're talking about here. I know this is a bellyful that, that we're getting for sure. But just as an example, I have something to do with the little airport on the Sunshine Coast, area called Seashell. It's just northwest of Vancouver. And they recently had a runway extension there. The runway was about 800 feet were added to the runway. And there was some landscaping required for that. The material is a glacial deposit called till. So that's just a sediment that is deposited underneath ice by the action of ice. And it's relatively easy to excavate, but there's also bedrock. There's granite under that till, and that had to be blasted in order to get the grade for this runway extension. Well, if the contractor hadn't realized or hadn't thought, well, this till isn't going to go on forever. So maybe because we have some understanding of the geological history in this area, we can anticipate, well, maybe we're going to hit bedrock. That's going to be a lot more expensive to deal with. So if that had been a surprise, it would have been a big surprise financially. So understanding the geology, especially in an area like Canada, where the last ice age has been so responsible for producing the material that you're going to be standing on, building on, and so forth. There's a lot of practicality in understanding the geology. So getting to eskers and kettles, those are geomorphic features, and they're a product of the retreat stage of any glaciation. And of course, in our case, it's the retreat of the last ice sheet, the one that I keep saying it was at its maximum extent 18,000 years ago. So as that ice began to melt, a lot of the water would flow underneath the ice, so between the ice and whatever material the ice is resting on, and it would form channels in the ice. And of course, remember that, we're just talking enormous quantities of water here. If you're lucky and flying across the prairies, and you've got a clear day, you can see the meltwater channels. They generally have a tiny little meandering stream in them, but there'll be channels maybe 2 kilometers wide, just snaking way off to the north. Those are meltwater channels, so those would have been major rivers at the time of the decline of the last ice sheet. At any rate, there was this water flowing under the ice and moving enormous amounts of sediment, so it would fill these underwater tunnels, if you like, with the sediment, sand, gravel, boulders, and so forth. And of course, once the ice left, that would be left as a ridge. So that's the formation of an esker. And then a kettle, well, eventually the ice would become stagnant. Like it just wouldn't have the elevation increase to the north to make it flow. So it would stop flowing and it would just sit there and melt in place. There was still lots of water flowing around, and so some chunks of ice would get buried by all this sediment being brought, and of course eventually thaw and leave a depression. and that's the formation of a kettle. And quite
Yeah, these lakes are so interesting because they, like, again, like a ice cube that was buried there, and they make these depressions. They have steep. You can see the glacial till bend and how they're formed, but they're mostly still spring fed, so to speak. But that's a couple of names of the parks. And the other thing too, when we tour around Northern Ontario, and we're really, we really are on a tour, then all of a sudden you drive up Highway 11 North and you come over the hill, and lo and behold, there's the little clay belt of Temiskaming Shores, New Liskeard, and the like. Then go a little further and you get between Kapuskasing and Hearst, you've got the big clay belt. How did they get formed, Larry? Because those are farming areas. And again, when we look at our most recent humankind history, from First Nations Indigenous into the first colonialists, the settlers, of course, it was all about the land grants of broken promises and shattered dreams. It was your bad day to be on some aspects of the shield. But if you got into those little clay belt and larger clay belt of Hearst and Kapuskasing, you might be able to eke out existence. And now, today, as the climate warms, this is becoming more arable land, and the growing seasons change. They go right back to what Larry said at the beginning. And of course, we have great influx of Mennonite people into both of these areas. But how did those areas get formed, Larry?
Bill, just another episode during the retreat of the last ice sheet. And one thing one has to remember is that, again, getting back to this phenomenon of the crust being pushed down by the weight of the ice. So you kind of had if you like, a moving moat, low area around the edge of the ice sheet, and that would fill up with water. And as the ice retreated, the land would rebound. So you had a whole series of temporary lakes sort of following the retreat of the ice sheet. And the clay belt was just one of those. So you'd have a large area of standing water. It could be, up to hundreds of kilometers long and tens of kilometers wide, like sort of almost like an inland sea. And again, along with all this meltwater and moving of sediment, those temporary lakes would fill in with sediment, silt and clay, and form and so form the areas the flat areas that we see today in the clay belt. And there's all sorts of examples of these across the prairies as well. Like around Regina, it's billiard table flat there. So that would have been a temporary glacial lake in that area as well. And generally, arable soils.
Now, this has been a real education for Ben, for sure. And,
yep.
And I know he's going to ask a question. But my another question, yesterday I came back from a 2-day mining tour at IM Gold, which is near Ogogama. It will become the second largest open pit gold mining operation in Canada. And, of course, it's in Northern Ontario. And we have the Timmins camp. And, of course, we know much about the meteorite impact of the Sudbury Basin. And this gold goes across. It's not all discovered yet and will be discovered, and we've got the Ring of Fire. But why do we have, particularly the predominance of gold, but other precious metals? How do we rationalize that when we're talking about geology, geomorphology, and what we have in Northern Ontario? Because it's such a contributor to the Ontario economy, and particularly now as we move into that whole era of electrification and what we need, palladium and the like.
Oh my gosh, Bill! Gee, we'd need a whole university degree to answer that question. But in general, mineral deposits are formed by a process of segregation. So what and I mean, I'll just go through a really general example here. When you have a major igneous intrusion. And I mean, the Canadian Shield is just full of those. Okay, so you have a crystallization period of time. So this would be the formation of what we call a pluton, which is just a large area of magma, so molten rock, which has solidified deep underground. So that will happen, and there's a whole sort of crystallization series. The quartz and feldspars tend to crystallize out first, and then you've got magnesium, iron minerals. They form the darker silicates, and they crystallize out. And when this process is near to completion, you still have what we call a volatile fraction. There's water in there. Lots of water. And of course, it says superheated steam. And so the availability of that water means that there's a lot of things that can remain dissolved or held in dissolution, in suspension in that water. And of course, this is a cooling process that's going on. So there's contraction and fractures are going to form. So this volatile fraction, which will contain all sorts of things, metals, zinc, copper, lead, gold, and whatnot. So the remaining fluids associated with this intrusion are going to shoot into these fractures. They're under high pressure and form veins, and there's a lot of sulfur as well. So I say, these volatile components. So they're components that can stay mobile after most of the silicates have become solid. So it's a concentrating process, and so you get what we call a hydrothermal deposit. So hydro, that's water, thermal, hot. And so these are hot fluids, water-based fluids that contain this concentration of typically sulfides. So we get the pyrite and the galena and the chalcopyrite and sphalerite, the zinc sulfide and so forth, and along with smaller amounts of silver and gold and so forth. So that's a major sort of ore body forming process. And of course, the trick, the exploration geologist is going to be looking for clues that suggest that this kind of process went on in this particular area. Now, sometimes like Timmins, for instance, where you've got thick glacial deposits, you don't get to see a lot of bedrock, but you can use other techniques because these sulfide accumulations, they'll have different geophysical or physical properties from the surrounding rock. For instance, it'll be more electrically conductive, so you can use an electromagnetic survey where you induce a current or a field, electrical field in the earth, and you'll get a return on that, and you'll be able to measure the conductivity. And if you find a conductivity zone, that could be a target for exploration. And I think that's actually how the Timmins Kid Creek mine was found.
North Bay Echo is proud to partner with Twigs Coffee Roasters, a part of the community since 1995. Twigs offers a wide selection of quality beans, fresh roasted in-house every day. Find your favorite specialty drinks at our espresso bar. Rejuvenate with freshly squeezed juice, or treat yourself to mouth-watering selections from our gourmet deli. And don't forget our irresistible fresh baked goods, including uncompromising gluten-free options. Twigs has 5 locations to serve you, from North Bay to Sturgeon Falls to Sudbury. Order online for pickup at twigs.ca. And coming soon, you'll be able to order fresh roasted coffee beans direct to your doorstep from our distribution center in North Bay.
Looking over at Ben now, talking about segregation and unconformity, all these terms. I know it's like you're looking at us like we have 3 heads, but Larry, he's a true rock star, you can tell.
I was going to make a rock pun.
Yeah, well, you can do that, but you might have when we're heading to the end of this, where it goes by so quickly, but you might have a question or something that, fascinates you from a perspective. Again, people need to know what they're looking at because it's a long process, and we call it scenery and vistas and trails, and of course vegetation grows on, and of course we take all this for granted, and I don't think we really should, and we have to go back into our initially our high school career, did we remember any of that? And probably the answer is no. And unless we take some, some graduate work in some of these subject areas like geomorphology, fluvial geomorphology, and the like, that
stop adding words to it.
So Ben, over to you, and we'll take this. We'll tie all this and tie a ribbon around this rock episode.
I think the last time I heard like igneous rock and metamorphic
and sedimentary,
I think that was honestly probably like grade 10 science class.
Yeah, well, that is. It actually starts now in the grade 5 curriculum in Mining Matters, which is the educational wing for educational resources for teachers. So yes, that starts with basic, and again, the reason we have mining tours at the Canadian Ecology Centre, and we've been doing them now for 16 years, is that if it's not mined, it's grown. And if it's not grown, it's mined. Everything in this room, everything in your house, Larry's house, everything around us really falls into those two areas. Yes, we can create things synthetically, but really we have to really know about the rocks, the minerals.
Yeah, so the thing that was kind of bumping around in my head for most of this time was talking about, I guess, the future, because a lot of geology, you're looking at the past and you're looking at it. There's kind of two lenses to look at it. There's like the human lens where we can comprehend like how long stuff is. And I think humans have only been around for 30 or 50,000 years. Mm-hmm. And then there's the actual Earth timeline where you're talking about millions of years and billions of years. So Larry, I kind of had a twofold question, and it's just taking a look at geology's impact. I wouldn't say geology's impact, but from a geologist's standpoint, what is the future going to look like, I would say, in human years in the next few hundred years or so, especially like kind of in the North Bay, Northern Ontario, the big changes that will happen geologically, and then also into the future, into the longer time change, as we get climate change and as things happen, what do you think is going to happen kind of in the future and how our world is going to change?
Without talking about the moon, because we're going to go to the moon very soon and start mining there. Yeah. But over to Larry.
Yeah, or what about geomorphology on Mars?
Exactly.
At any rate, yeah. Oh my gosh, Ben. I mean, the changes that we're going to see are going to be a function of what happens with the climate, because I mean, the climate is the force that alters the surface of the earth, through erosion and so forth. I mean, we've just had an example here in the Lower Mainland of Vancouver over the last few days. Over the last weekend, we record the rainfall. We had 252 millimeters of rain in 2 days. Now, when we had this big flood 3 years ago in November, and we measured 170 millimeters of rain. So what was happening on the North Shore? So there's a mountain slope immediately north of Vancouver, which has about 250,000 people on it, and there's all sorts of little streams that drain down through these residential areas, and of course normally they're benign, but most of them jumped their banks and started flowing down the streets and of course into people's yards and bringing all sorts of debris. And okay, we can attribute this to climate change and so forth, and there may be some truth in that, because I mean, the Earth's climate is warming. As the atmosphere warms, it can hold more moisture. And so when we have a system bringing in a lot of moisture that's going to fall as rain or snow, it was all rain this time. If there's more water in the atmosphere, we're going to get more rain. But at the same time, of course, urbanization, where the housing areas are spreading higher and higher up the hillsides, restricting the drainage. So there's an interaction here. And the trouble is people have short memories and with flooding and so forth. And so if you go for a period of a few years without anything happening after a severe damaging event, people forget about that and just keep on building and so forth. I mean, we see the same thing in the Gulf Coast of the U.S. with hurricanes, and we've had a couple in the last month down there. So yeah, I mean, it's a tough question to answer, but I think what we're going to see in the next, decades and centuries, we're going to see effects of climate change. It's hard to say what they'll be, but I mean, that's a geological force for sure. I mean, running water is a geological force, or lack of water. I mean, that's a geological force too. And so in terms of geology, it's going to be what the climate does to us, that's going to control the geology. I mean, I guess the other major geological effect that we see, certainly, well, I mean, at places across Canada, but certainly on the West Coast, of course, are earthquakes. But I don't think you can attribute those to climate. That's strictly a function of what's going on in the mantle of the earth and so forth. But I mean, it's something also that we're more and more concerned about with urbanization. More and more people living in areas, building, of course, and maybe forgetting about the last big earthquake. And that's where regulation comes in, that you have to have building codes adjusted. And the Canadian Building Code is constantly being adjusted to take into account the latest understanding or improvements in understanding of seismicity. So that's a lot of talk.
We've talked a lot about things today, and as we wind up here, Ben, again, we just can't. The only part of our body is our feet that attaches to the ground all day long, every day, and of course, we need to know about the ground. And I think we've covered a lot of ground, and with Larry, and we really thank you. But I'll turn it over to you, Ben, for last thoughts as we. Leave the rocks behind, but we can never leave the rocks behind. That's why I collect rocks, and my whole yard is full of rocks. I give people rocks. There's a lot of energy in the rocks. Rocks actually grow, but that's another thing to talk about. But
how do you end the episode off with rocks also grow?
Yeah, well, that's how we got to go. It's true, eh, Larry? Just say yes. That's true. The rocks grow.
Well, they do.
Indigenous people will tell you for sure rocks grow because it's all part of cultural teachings.
Okay, so we do have to wrap up, but here's the thing that I need to know from you, Larry, before we go. What is your favorite geology or rock pun?
Oh my gosh. Oh well, there's
probably a book.
Well, there's a geological feature, a rock feature called a joint, place where rocks get together. But what the best little story I like is, I don't know if you've ever heard of it, but there's a little principality called San Marino in central Italy. And, they issue their own stamps and so forth. And it is on a geological feature called a Klippe, and it's a German word, and all a Klippe is an isolated piece of rock, or or an element of rock that has been moved along a fault laterally. Okay, but it's become isolated, kind of like a mesa by erosion. So one wonders if there's going to be future UN debates about one country literally overrunning another.
That's a good.
That's a good one.
That's a good place to end. Okay,
I'll leave it at that.
Right.
And of course, there's Bill. I'm sure you've come across this. The rock type called leverite. And so you tell your helper that's with you, that's a piece of leverite. Leave it right there.
Awesome, that's amazing. Thank you so much, Larry, for joining us.
Oh, thank you for the opportunity. Always love to talk about geology.
Well, big thank you to Larry for coming on the show for the second time. And I said this during the one ad read, but it did feel like I was back in grade school, back in college, in the best possible way too. It was just a lot to process, and as I've been editing through this video as well, getting to go back and revisit some of this stuff and let it soak in again. I kind of, if this kind of felt like it went over your head, give it another listen. And I'm not just saying that for the stats. I'm saying that because it actually will help you soak it in again. But again, Larry, incredibly smart. He gets an A+ for me on his pun game, which, let's be honest again, it's the most important thing. So if you want more of the Backroads Build podcast, if you enjoyed this episode, you can find us everywhere you get your podcast. The video version of this podcast is on the North Bay Echo YouTube channel. And of course, always on NorthBayEcho.ca. And of course, please leave us a comment or review on your preferred platform, wherever, whether it's Apple or Spotify, or you go on YouTube. Just leave us any sort of feedback there. It lets us help us grow the show. It lets us know what's going right, what's going wrong. Please let us know. And don't forget, new episodes of this podcast drop every single Wednesday morning. And finally, check out NorthBayEcho.ca for a whole bunch of other local podcasts. Of course, the way the media has been going the last, decade or so, a lot of the smaller communities are getting less and less of a voice. And it's getting harder to get some of that local news out, to get some of that local feel out. And that's kind of our mission here at Echoes. So all of our podcasts, it's all about making sure those local voices get heard. It's all about issues and people and all this stuff in the community that we're trying to do. So check us out at NorthBayEcho.ca if you want to get more of that. So that wraps things up with us. We will see you next Wednesday for yet another Backroads adventure. This weekend, make your way to Casey's Restaurant in North Bay for an unforgettable get-together. Dive into our delicious appetizers and enjoy the best drafts in town. It's the perfect spot to unwind, catch up with friends, and savor great flavors. Don't miss out on the fun. Join us at Casey's for a weekend filled with good food, great drinks, and even better company.